Hello everyone and welcome for this presentation about our conference paper entitled Anchor-Based Haptics, Portable Interfaces Leveraging Real Surfaces to Display Grounded Force for 3D Shape Simulation in Virtual Reality. Nowadays, virtual reality is increasingly used in different fields such as engineering with virtual prototyping, artistic fields with virtual sculpting, for instance, or vocational training to different jobs such as surgery. For these applications, it is interesting to feel the virtual shapes. This raises the need for shape simulation in virtual reality with haptic interfaces. To simulate shapes in virtual reality, researchers have investigated different haptic interfaces, including both grounded and portable haptic interfaces. Grounded haptic interfaces, such as fixed robotic structures or encounter-type haptic interfaces, are the most efficient solution to display grounded shapes, because they can display grounded forces very convincingly, and but this solution have a limited workspace. Such limited workspace may limit their usability when it comes to simulation in large-scale spaces. On the other side, portable haptic interfaces can be used in a theoretically infinite workspace, but often struggle with displaying convincing grounded forces because they can also generate forces between different body parts. So, in this work, we wonder if we can propose a compromise between these two approaches to simulate grounded shapes in virtual reality using portable haptic interfaces. To do so, we propose in this paper an approach that we call the anchor-based haptic approach. It consists in using portable interfaces that make contact with grounded surfaces when there is a need for grounded force feedback in virtual reality. For instance, here we have a virtual cube and a virtual handle. When there is no contact between the virtual cube and the virtual handle, the interface is not in contact with the table, so the user can move freely around the cube. When the user comes in contact with the cube, the interface makes contact with the table to prevent the penetration inside of the cube. So the shape of the cube is simulated by the interface. And thus, we define the concept of anchor-based haptics as follows. Such interface should be handled or wearable. It can give its user a force feedback when in contact with a real surface, and its contact with the real surface can be released when no haptic feedback is needed. The surfaces to make contact with can be found anywhere. They can be walls and grounds, for instance, or office furniture such as a table or a chair, and they can even be the user's body, for instance, to simulate the shape of a dissimilar avatar. Interestingly, in the literature, we found another interface that comes inside of the scope of anchor-based haptic interfaces, which is the fingertips. It consists in different height mechanisms at the tip of each finger to simulate the shapes in virtual reality. To illustrate this approach, we designed two haptic interfaces. The first one is T-Eng. Similarly to fingertips, it simulates different heights, but with a wider stroke to simulate bigger shapes. It consists in a modulus at the end of a VR controller, which uses a reel-based mechanism to extend the distance between the controller and a bottom platform. So the bottom platform can make contact with a table or the ground or the body or any surface to simulate a virtual shape. The second interface that we called arrange uses two concurrent actuated axes to simulate orientations in two directions of freedom. With such interface, we can simulate the orientation of the contact between the virtual handle and a virtual shape, and thus simulate the shape with orientation-only feedback. Interestingly, unlike other existing approach that simulate only orientation in a tactile way at the fingertip, this interface can simulate orientation in a more kinesthetic way by moving the whole hand. The two interfaces are tested independently. They are compared with vibrations. Vibrations is chosen as a baseline for being easily displayable within portable interfaces and being widely used in virtual reality. 12 participants have been involved in each experiment. They were placed in front of a table, which is used by the interface to display grounded forces. They have tested different use cases for each interface that I will develop later. Each interface and vibration are evaluated with using 1/7 Likert scales in terms of multisensory coherence, realism, helping to complete the use case, and being liked or disliked by the participants. You can find the full protocol in the paper. For T-Hang, the use cases include the touching the different steps of a stair, what we call discrete exploration, continuously exploring the slope, that we call continuous exploration, manipulate cubes and touch those cubes once they are stacked, and continuously touching some objects that are more or less soft, and compare with a solid block. And so the results suggest that T-Hang improves the continuous exploration of shapes and the feeling of softness compared to vibrations. For R-Hang, the use cases include simulation of OK to simulate collisions with slight back and forth rotational movements, the continuous exploration of both a VAT and a bump. The results indicate that R-Hang is better than vibrations to simulate continuous exploration of a shape, but it's not relevant at all to simulate collisions with an object. So to conclude, in this work, we have formalized the anchor-based approach and illustrated it with two examples that we called T-Hang and R-Hang, and simulating respectively some translations and rotations. Our experiment suggests that this approach is promising for applications where continuous shape explorations occur in a large workspace. Future work could lead us to improve both interfaces and mix them to simulate simultaneously translations and rotations, and maybe compare it or mix this approach with redirecting, touching, and walking to lead people to the walls and compare the touching of the surface itself and the use of the interfaces. So here are the references, and thanks for your listening.